Hi everyone, welcome back in this series of videos. So like I said, it is a series of videos. We will be talking more about resonance forms. So before you watch this video, you should watch the introductory video on resonance, which is more of a PowerPoint that takes you through what resonance is and what resonance forms are, what is a resonance hybrid. It sort of gives you an overview of the whole concept of resonance. And so just to quickly review, resonance to an organic chemist or a chemist in general, resonance addresses inadequacies in bond line structures or Lewis structures in some sense. Okay, so when one Lewis structure cannot fully explain the bonding in a given molecule or a species. Okay, so then resonance comes in handy because we can draw several Lewis structures for the same molecular species or compound or the molecule, and those different structures that we draw are called resonance forms. Now, the big difference, as highlighted earlier in the previous video, is that resonance forms only differ in the distribution of electrons. And those electrons are usually lone pairs or pi electrons. Now, the lone pairs could be a lone pair, or it could also be a negative charge on an atom. And we're going to see all of this in detail in this particular video. So important thing to remember is we will never touch sigma bonds. Okay, we are not going to break any single bonds when we do resonance. And so, like I said, the previous review, the previous video, the introductory video, sort of goes over some of these things. So please watch that video before you get started on this video. So the plan for this series of videos is to actually take you step by step through the process of constructing resonance forms. I know a lot of textbooks and other resources actually refers to it as just drawing resonance forms, and I think that's a very colloquial way of saying it. But I think the process of drawing resonance forms is more of constructing something. That means it's a higher order thinking that you're putting into it. Okay, it's a higher order skill that you have to draw, that you have to basically engage in. So what we're going to do is we're going to start by defining some of the ground rules in terms of what's allowed, what's not allowed, you know, and if you have a structure, what sort of a resonance form can emerge from there. Okay, so the first category of structures that we're going to look at for which you can draw a resonance form is when you have a pi bond. And so when we have a pi bond, you have to realize this is part of a double bond. Okay, this is part of a double bond because you cannot have a pi bond by itself. A pi bond is always, it always exists in addition to a sigma bond. So when you have a pi bond between two atoms with differing electronegativities. Okay, so that's the first scenario that we're going to look at. Now, since we are talking about organic molecules, we wrote two atoms with different electronegativities. So we are going to look at examples where one of these atoms, where at least one of these atoms is a carbon atom. Okay, and it can be extended. Once you understand it, it can be extended to like other sets of atoms. Okay, so let's draw out our example. So let's say we have a molecule like that. Okay, that's one structure that we're going to look at. And another structure that we're going to consider is this molecule. Okay, so we have two structures that we're going to we're going to consider as part of this first criteria that we're going to look at. So notice how you have, in the first structure, you have a double bond between carbon and the oxygen atom. And as a quick review, going back to bonding, the double bond constitutes one sigma bond and one pi bond. Okay, so there is one pi bond between carbon and another element, which is oxygen here, and oxygen is more electronegative than carbon itself. Okay, so in this scenario, what we can do is, and in fact, actually, before we go into that, let me talk about some of the other finer aspects, more like a review. Notice how the octet is complete for all the atoms here. So this carbon has 2, 4. These are bonds, and each bond has 2 electrons. So it has 2, 4, 6, and 8 electrons around it. So the octet is complete for this carbon. The oxygen has 2, 4, 6, and 8. So 8 electrons around it. So as far as carbon and oxygen are concerned, those two atoms, their octets are complete at this point. Okay, and let's talk about the bonds themselves. Again, a quick review. There are 2 bonds here, one sigma bond and one pi bond, okay, whichever way, but there are 2 bonds, and there are 4 electrons total for the 2 bonds combined. And of those 4 electrons, remember that 2 electrons are contributed by carbon, 2 electrons are contributed by oxygen. So that's the situation, the ground scenario sort of here. Okay, so that is where we're starting now. Okay, so in a situation like this, or in a scenario like this, when you have a pi bond between 2 atoms with different electronegativities, oxygen is more electronegative than carbon. What we can do is we can take the pi bonded electrons, okay, the pi bond, the electrons and the pi bond. And again, we don't know which one is the pi bond. One of these bonds is a pi bond, the other one is a sigma bond. So what we can do is the pi bonded pair of electrons, and I'm going to just assume that this bond on the right is the pi bond. I could as well do it on the left, maybe do it on the left, doesn't matter, okay? I'm going to assume that this bond on the left is the pi bond. So when you have 2 atoms that differ in electronegativities, what you can do is you can take the pi bonded set of electrons and move it to the atom with a higher electronegativity. That is how you do it, okay? So you would not move the electrons to the atom with the lower electronegativity. So in this particular case, let me write it here, or with a different ink. I just want to label this for you, that this is a higher electronegativity, okay? So oxygen has higher electronegativity, and so what we did is we took the pi bonded pair of electrons and transferred it to the more electronegative element, okay? More electronegative element. And again, just as a quick review, I want to talk a little bit about the arrows that we use for these resonance forms, so drawing resonance forms right now. What we are doing is we are moving the pi bond. The pi bond should have 2 electrons in it. So we're moving 2 electrons from between carbon and oxygen to the oxygen atom. And so for that reason, I'm using a double-headed arrow. My arrow has 2 heads. That implies 2 electrons, okay? So 2 electrons for the double-headed arrow. And since I'm moving electrons from the pi bond to the oxygen atom, my arrow starts from the center of that pi bond where the electrons are. So that's the source of electrons. The arrow starts from the source of electrons, and the head of the arrow points to the atom where the electrons would eventually end up, okay? So let's draw the resulting structure. So when I do this, the structure that I should get will now have a single bond between the carbon and the oxygen atom. Okay, there were two bonds before, but now it should only have a single bond. So that's the sigma bond. And oxygen, to start off, had two lone pairs. We've moved another pair of electrons to the oxygen atom. So now that oxygen should have three lone pairs on it. Okay, it should have three lone pairs on it. That's the structure that we're going to get. But it is missing formal charges at this point. So you can calculate formal charge and for the carbon atom and for the oxygen atom. Okay, so if I have to calculate the formal charge for the carbon atom, so over here, formal charge should be carbon's valency is 4 or group number is 4 minus, there are no lone pairs on it. Okay, so 0 minus half of the bonded pair of electrons, and there are three bonded pair of electrons, so that's 6 electrons, 2, 4, and 6. So half into 6, this comes out to 1. That means this carbon would have a positive charge on it. Similarly, we can calculate the formal charge for the oxygen atom. Okay, group number is 6 minus number of number of lone pair electrons or non-bonded electrons, whichever way you call it. So there are 2, 4, and 6 lone pairs on that oxygen or non-bonded electrons. So I'm going to put 6 minus 6 minus half times the number of bonded pair of electrons. So we went through the math already. So the bonded pair of electrons is 2. So half times 2. And so this comes out to minus 1. So that means this oxygen should have a negative charge on it. That's the structure that we're going to get. And now this resonance form is complete. Now, you could arrive at these formal charges without, qualitatively, you can actually arrive at the formal charge without going through the math, because going back to the structure here, realize that we are moving one pair of electrons, one bond to the oxygen atom. This bond has two electrons. One of those electrons was contributed by the carbon atom. The other electron was contributed by the oxygen atom. So when we take the pair of electrons here and put it on the oxygen atom, oxygen now has an extra electron, an additional electron, because it got the electron that was contributed by carbon atom. So it will have a 1 negative charge. Similarly, carbon lost the electron that it contributed towards that bond, so it will have a positive charge. Okay. Now, since these are resonance forms are shown using this double-headed arrow between them, and you enclose these within square brackets. Okay, so that would be the resonance form in this case. I took a lot of time, just to explain what's going on, but we'll go through the same process quickly in this next one. Okay, so let's look at this next set where again we have a pi bond between two atoms with different electronegativities. So we have a carbon and we have a nitrogen atom. So nitrogen is more electronegative than carbon. So what we can do is we can take the pi bond. Okay, there is a pi bond between the two atoms. So we can take the pi bond and move it to the nitrogen atom. Again, pay attention to the arrows. The arrows are really important when it comes to resonance or when you show electron movement. The arrow starts from the source of electron. It points to the atom or to the position where the electrons are going. Okay, we get that. So now we can draw the resulting resonance form. Now there should be a single bond between carbon and nitrogen. The nitrogen would still have this methyl group on it. So this is a methyl group, this is a methyl group, that's a methyl group. Okay, just some review. The nitrogen had one lone pair on it. We moved another pair of electrons. So it should now have two lone pairs to it. And like we did here, since there were two electrons here, one from the carbon, one from the nitrogen, and both electrons were pushed to the nitrogen, this carbon would end up with a positive charge on it, and the nitrogen would end up with a negative charge on it. These two are resonance forms within square brackets. Okay, so that's how you would do resonance when you have a pi bond between two elements that differ in electronegativity. And like I said, once you understand this, you practice this a little bit. Right now, we've limited ourselves to carbon double bonded to something, but you do not have to be limited. If it's a double bond between a nitrogen and an oxygen atom, oxygen is more electronegative, you can do the same thing, okay? So that's the first scenario. Okay, let's go to the second scenario, which is the reverse of this. Okay, so we're going to look at something that's the reverse of this. So the second scenario where you could do resonance is when you have, or when there is a lone pair. Now read this as an electron pair. Okay, when there is a lone pair adjacent to a C plus, okay, a carbon with C with a positive charge. Now, this can be generalized to any atom bearing a positive charge, okay? And I'm going to draw again examples, and I think as soon as you see it, you should be able to make a connection. So let's look at this. And I'm just going to draw some slightly different structures, so that you see some variety, although it's not that complicated, okay? So I'm going to draw a structure where we have this, we have an oxygen atom. This carbon here has a positive charge. So when the positive charge is written next to that carbon, that means that carbon has a positive charge. Oxygen has 3 lone pairs on it, which means this oxygen should also have a negative charge. Okay, and then the second scenario that we can look at is sorry. Let me draw something different. Or in fact, actually I want to keep it simple, and then I will show you a complicated example also. Okay, let's just keep it simple and use the molecule that we just had. Okay, so 2 examples to start off with. What we have in the first example, again, connected what's written here. So we have a lone pair. This oxygen here, this has 3 pairs of electrons. Okay, it has a negative charge. That is a formal charge, but if the charge were not there, we were going to call this lone pairs. Okay, so it's a lone pair adjacent to a C plus. So if you notice, the lone pair is on an atom that's adjacent to a carbon that has a positive charge to it. So in this particular case, now if you look at it, the oxygen has several pairs of electrons on it. The carbon has a positive charge to it. So whenever you have a scenario like this, the most common, the obvious thing to do is to take one of these lone pairs. Okay, you could take any one of these three lone pairs and move it to the space between carbon and oxygen. Again, I want to highlight the arrow itself here. So what I did is I took the lone pair from the atom that's next to the positive charge and moved it to the space between that atom and the carbon atom. Okay, and so my arrow, it's a double-headed arrow because I'm moving two electrons. Okay, so it's a double-headed arrow, and my arrow starts from the lone pair or from that pair of electrons, and it ends, it is pointing towards the space where those electrons are going. So let's draw what would be the resulting structure. Okay, so once we do this, there was one bond between carbon and oxygen already. We took a pair of electrons, moved it to the space between carbon and oxygen. So now there should be a double bond. So we should have two bonds now. And oxygen had three lone pairs, but we moved one already. So now oxygen should only have two lone pairs on it. And that will be the resonance structure. And I would encourage you to actually do formal charge calculations, okay? And what you should arrive at is there is no charge on either of those atoms, okay? And now again, intuitively, if you think about it, there was a negative charge and there was a positive charge. When you combine a negative charge and a positive charge, you should get zero charge, okay? So there's no charge. So these are both resonance forms of each other and can be enclosed in square brackets. Now, if you notice, whatever we did here right now is the exact opposite of what we did in scenario one, okay? And this example is exactly the same as what we had in scenario one. Again, we have a carbon with a positive charge. There is an atom which has lone pairs on it adjacent to that carbon. So you can take one of these lone pairs, move it to the space between carbon and nitrogen. Again, my arrow starts from the source of electrons and ends to the sink, or where the electrons are going finally, okay? And so the resulting structure is going to be double bond between that carbon and nitrogen. The methyl's going to be there, and the nitrogen should be left with one lone pair on it. Again, no charge over on any, no formal charge on carbon or nitrogen. And these are both resonance forms of each other, okay? So now, within this scenario here, let me show you the other example that I was drawing, okay? So let's say we have a scenario like this. That. Now, if you notice, in this scenario, I have a carbon here with a positive charge on it, and there's an oxygen with lone pairs on it. There's another oxygen with lone pairs on it, which means in principle, I could use either one of these lone pairs. And I'm going to show you what happens when we use both, because they would both result in a resonance form, okay? So let's say if I use this oxygen at the top, or the lone pair on that oxygen at the top, one of the lone pairs on that oxygen at the top, and I move that lone pair to the space between carbon and oxygen. So we've got we had three lone pairs on that oxygen. We moved one of the lone pairs down to make a bond. So I'm going to draw the resulting structure onto the left side here. Got that. There was single bond between carbon and oxygen. That is now a double bond, okay? Two bonds. Two bonds and three pairs of electrons, which becomes two pairs now. And again, since there was one positive charge and there was one negative charge, no charge overall. Now, I would suggest that I would recommend that you do formal charge calculations till you become comfortable identifying these patterns, okay? And whenever you're comfortable, then you will basically be drawing these things like right off the bat, okay? When you see a structure, you'll be able to draw it. So these are both resonance forms of each other. But like we said earlier, there's another oxygen atom with a lone pair next to this carbon, which has the positive charge. So we can draw another resonance forms because I can take a lone pair from that oxygen and move it to the space between this carbon and oxygen. Now notice how I didn't take those electrons and move it to the space between the other oxygen and that carbon. That's not what we do, okay? We take those lone pairs, move it to the space between that element with the lone pair and the carbon with the positive charge. So when we do this, we should get a structure where we have carbon, and since we use this lone pair to make the new bond, this bond here should still be a single bond. That oxygen would still have all three of its lone pairs and hence the negative charge. On the other side, we should now have a double bond, and this oxygen to the right, bottom right, it used one of its lone pairs to form that new bond. So it should only have one lone pair left on it. And it would have that other methyl group on it, okay, the CH3 group on it. So now, once you do formal charge here, what you would realize is this oxygen now should have a positive charge on it, because an oxygen, when it makes two bonds, it should have two lone pairs to it. But if an oxygen has made three bonds and it has only one lone pair to it, it should have a positive charge. Okay, so that's just a common bonding pattern. Again, something for you to recognize, and you've probably already recognized this through, you know, the homework that you've been doing. So the positive charge now ends up on the oxygen. All of these three are resonance forms of each other. Okay, these three are resonance forms of each other. So we can enclose this entire thing within square brackets because these are three resonance forms of each other. Okay, so that's scenario 2, where you have a lone pair adjacent to a carbon which has a positive charge. So the other scenarios will be discussed in subsequent videos.